Okay, folks, chapter 5 of the 7th edition of the NASM Certified Personal Trainer Certification Course Workbook. And chapter 5 is the beginning of section 3, which is the basic and applied sciences and nutritional concepts. We are now basically in this textbook moving into sort of the meat and potatoes of what most folks would consider to be part of the personal training repertoire. So understanding the nervous, muscular, skeletal system. So that's why we're really starting in section 3 is where we're really beginning now to get into sort of the heavy lifting of memorizing and understanding some concepts about anatomy, physiology, and of course in this section, this entire section of these chapters 5 through 10, is really going to also give us nutrition and supplementation. But right now in chapter 5, we're going to start with the nervous, muscular, and skeletal systems. Remember, of course, as always, to have a pad and a writing implement. This is obviously really critical once we start this section and the subsequent chapters, that you're going to really need to be spending a good amount of time writing, rewriting, speaking it out to yourself, read, write, recite, to memorize this information. And if you're not familiar with anatomy, basic anatomy, physiology, this is where you're going to have to spend a little bit of time, obviously, in chapter 5. So we start out with introduction to the human movement system, and that's been sort of coalesced into these three basic functional systems in the body. It's called the HMS, human movement system. So if you see HMS, that's basically what we're talking about. And the human movement system is comprised of the skeletal system, the muscular system, and then the nervous system, which is what functionally operates the muscles. And then the muscles work over the skeleton, and the skeleton has joints, and that's how you create movement. So the human movement system, the learning objectives in chapter 5 is to just basically to understand the basic structure and function of all three of those, the nervous, muscular, and skeletal systems, and to understand joint types from the skeletal system and muscle fiber typing, things like that, and then identify the effects that exercise has on each of those components, because training exercise, whether it be cardiovascular or resistance training, is going to affect all three of those systems in varying ways and levels. And so we definitely want to know what those effects are. And so an introduction to the human movement system starts out with the nervous system, and that's what we're going to see on page 117. As always, you have sidebars. Please remember to write down those definitions. They're helping you out by telling you these are some key terms to remember through the chapter. So the nervous system starts out anatomy of the nervous system, and the fundamental unit of the nervous system is the nerve cell or the neuron. And just keep in mind now, as you get through chapter 5, there's lots of drawings, lots of figures, a good amount of charts and some tables. And you really want to be able to, from my perspective, from a teaching perspective, I always like students to be able to draw, to really kind of internalize some of these concepts. And drawing things out is actually really very helpful. I've hooked up my my electronic drawing pad to whiteboard, and as I'm going through this and subsequent chapters, I'll try and help you out a little bit by showing you some drawings and ways that will help you to memorize some of these things. So on page 118, sidebar with lots of terms and definitions, and we have what's called the neuron or a nerve cell, and that's what figure 5.1 is showing you. All of those components of a nerve cell, the cell body, the nucleus, right, which is where all the DNA is, and that's in any cell, by the way, the nucleus of a cell. And then you have the axon of the cell, and that's where you have what's called myelin sheathing. And then at the end of the axon are what we call the synaptic terminals, which have synaptic clefts and then a muscle fiber that they're connecting to. So this is just a sort of a broad general overview. And so it's important to understand the basic anatomy of a neuron. So the central and peripheral nervous systems is how we break up the nervous system in general. So the general concept is you have the nervous system, but we look at the nervous system functionally, not just structurally, but functionally in two parts. One is the central nervous system, which is essentially, and figure 5.2 shows you it's the brain stem, and the spinal column. Now don't confuse when we're talking about the spinal column versus the spinal cord. So the nervous system is the spinal cord. In the skeletal system, you have the spinal column, which are the actual vertebrae, for instance. So the spinal cord are both the nerves and the nerve cell bodies, axons that protrude out of the spinal cord to all the muscles of the body. And so that's the spinal cord. So you've got to differentiate when we talk about the spinal column versus the spinal cord in the nervous system. We're just concerned with that grouping, it's almost like a band of all of these either nerve cells and axons of different nerve cells, nerve bodies that are located from the brain stem all the way down through the spinal column, right? And the spinal column basically protects those very delicate, very sensitive the spinal cord. So so figure 6.2 shows you the differentiation of the central nervous system, right? The brain stem, and spinal cord. And then what's called the peripheral nervous system, which is all the nerves as they exit the spinal cord. And so all of the nerve and all of the components of nerves that exit the spinal cord and actually go and connect to, in this case, the muscles of the body. It's a good idea to memorize some basic terms as well. Afferent versus efferent pathways. So afferent pathways are sensory pathways that will relay information to the central nervous system. Basically, what we're saying is that these two parts of the central nervous system have to communicate. Peripheral part of the nervous system, your skin, your muscles, they all have to send information to the central nervous system, to your spinal cord, which can then, in some cases, go up to your brain for cognition, things like that. Or it can go directly to the spinal cord and then have other information, or the efferent pathway going back out to all the organs and parts of the peripheral nervous system. And so you'll also get now into, on the bottom of page 119, the subdivisions of the nervous system, the autonomic and the somatic nervous system. So again, good idea to write this down: autonomic and somatic nervous system. But again, you have these definitions in your sidebars. And again, that's where you want to be looking first, right? Look at those first and write them down and make sure that you memorize them and understand them. Other concepts like mechanoreceptors, right? The Golgi tendon organ and the muscle spindle fibers. These are going to be spoken about to greater length, greater extent, as you get further along in the, particularly in the flexibility section, where you're going to learn a whole lot more about the Golgi tendon and muscle spindle. The somatic nervous system versus the autonomic nervous system. Figure 5.4 is a really good, helpful sort of visual to understand what we're talking about here. I would highly recommend that in this case, you go ahead and just write that out. Again, sometimes just writing words and definitions, that's fine to memorize it, but concepts like how the nervous system is broken down, for instance, into the central, and peripheral. And within the peripheral, you have sensory nerves, motor nerves, and that's an important important sort of visual to keep in mind. As you move into page 121, you'll see the difference between what's known as the sympathetic versus the parasympathetic nervous system. Again, take a step back for a second. We're already talking about a number of these different concepts that if you've never seen them before and you haven't studied this, you can already get overwhelmed. Again, the recommendation is that just take a, how do you eat an elephant? One bite at a time. Just take a little bit. Look at the somatic versus the autonomic and look at the distinctions and write them down and take a little bit of time understanding those. Then you can move into the sympathetic and the parasympathetic. It's really helpful to know these differentiations. And then now we move into the functions of the nervous system. Sensory function, and a key sensory function is what we call proprioception. Proprioception is simply how your body recognizes where it's at in time and space. Proprioception is, normally we talk about the muscle spindles and the Golgi tendon from a proprioceptive perspective. Again, big word, proprioception. Not really. It's just the ability to know, or your body's ability to know through the nervous system when things are moving, right? Where things are at. If I close my eyes, do I know where my hand is? Yeah, it's over there. Well, how do I know that? Well, I mean, I just saw it about 2 minutes ago, but no, from a sensory perspective, I have my eyes closed. How do I know my hand is over here and not over here? Right? Well, I know that because there are nerves, sensory nerves in the joints of my shoulder. There are nerves all throughout the muscles of my arm that are constantly telling my brain, hey, this is where your hand is, right? This is where your limb is. It's called proprioception. Okay. And it's one of the ways, even in this little box that they have for you, try this. Close your eyes, raise your left hand above your head, right? You can look through that. It's really important to kind of get a good appreciation for why these terms are, really important. And this is it, because when people are doing exercises, it's helpful for them to really know, feel, and understand what's going on while they're lifting or using resistance. So on page 122 now, we have another nice little figure here to help you understand a little bit about sensory nerves, right? Sensory input and then motor output. And that's really what this is showing you. Motor function. I see a glass of water, and that's what I'm seeing here in this. See a glass of water. I want to drink that water. Well, what do you got to do? The eye sees a glass of water. That's sensory input from the eyes to the brain. Your CNS interprets those senses, and then your hand reaches out, right? That's sort of the output, right? So the motor pattern then is instituted where I reach out, I grab the water, and I drink it. The mechanoreceptors, again, don't let the terms throw you off. Mechano simply means mechanical, right? Receptors are the nerves that, the nervous system component. Mechanical receptors, they're what's telling your brain or your spinal cord exactly what's happening inside the muscle or at a joint. The ones that we talk about are the muscle spindles, sensory receptors within the muscles that basically tell your muscles to contract. When they get overstimulated, muscle spindles are constantly under stimulation in a normal functioning muscle. It keeps the muscle tone, right? Keeps it in a mild state of contraction. Muscle spindles basically tell the muscle to contract when they get overstimulated, and there's reasons why that happens. That will get explained a little bit more in later chapters, but here's a good preliminary discussion or explanation, definition of these, and that's why chapter 5 is really important. Golgi tendon organs and other joint receptors are constantly sending information to the spinal cord, and then, depending on the mechanoreceptor, back up to the brain. for cognitive processing, and then back down if there's a motor response that's needed, then it will be implemented. And then there is the nervous system life course, and it's going to explain what's known as neuroplasticity. Really, a couple of really good books that I've read on neuroplasticity, and that's the ability of the brain to basically continue to learn. Now, their definition of neuroplasticity is the concept that the brain will continually change or grow, reforming neural pathways throughout an individual's lifespan. Here's the deal. The idea that you can't teach an old dog new tricks ain't true. Not when it comes to how the brain deals with the environment and mechanoreceptors and proprioception. No, it's actually interesting. Your brain can actually develop new neurological pathways, number one, and it can also work on reform the pathways that are already in there. And that's really important. That's really important to keep in mind. Neuroplasticity is a very interesting subject, but that's what this section is talking about. It gives you a little bit of insight into the reality that motor skill development can actually be learned at any age. It's the amount of time that you spend doing these motor skills that's going to strengthen the neural pathways. One of the reasons why, if you've ever learned to ride a bike, you develop motor skill pathways, right? You develop the ability, or your body's ability, to know when to contract and relax and what sequencing goes along with any type of movement on a bike, and maintain balance. You never unlearn how to ride a bike. And so I'm not saying teach people how to ride a bike. I'm just saying that's how this works. Neuroplasticity, this concept, lets us know, yeah, you can get people to learn how to train correctly, and you can get them to sort of reform and reroute neural pathways to develop motor skills. It's really pretty cool. So that's the nervous system. NASM gets into it enough, right? Gets into it enough to help you appreciate, as a trainer, what you need to know and what you need to do to help people. But remember, this is just the basic. The more specific, how we're actually going to do this, and the training and the programming, is what we talk about in later chapters. So NASM is helping us out here by giving us all this preliminary information that gets our brains sort of ready to tackle the more specifics. So it's important that we read through it and understand that. So now physical activity and the nervous system is going to be at the end, and of course this is motor skill development. You can go ahead and read on page 125 the development of motor skills. Right, there's 3 stages: the cognitive, the associative, and then the autonomous. And you can read those definitions. The skeletal system. A couple of things we need to know about the skeletal system as we're going through here. First is the division of the skeletal system. Just like we broke the nervous system into the central and the peripheral, the skeletal system we break into what's known as the axial and the appendicular skeletal system. Again, nice and easy to keep in mind. The axial skeletal system, the skull, the vertebral column, just as a for instance, the pelvis, and then the appendicular, right, or the appendages, right? So that would be, again, page 125, appendicular skeleton, the arms, legs, and the pelvic girdle. The axial skeleton is going to be the rib cage, the skull, and the vertebral column. And so, is it important to memorize that? You should just sort of know that as a sort of off the cuff piece of information, that the skull, the rib cage, and the spinal column, that's your axial, and then everything else that comes off at your pelvis, right? Your pelvic bone, your legs, and your arms are the appendicular. Bones and bone growth are really important, as well as the type of bones. You definitely want to understand that bones provide the leverage system for movement. We have joints that allow for rotational movement. And this is where a concept of torque and circular movement or angular motion occurs. Why? Because we have bony segments, right? It's one segment, and that's another segment, and they come together and they're held together as a joint. And so we have movement, right? Movement around the joint. I'm kind of watching this as I'm showing you, right? So movement around the joint, your elbow joint, right there, because there's a joint, one part of the skeletal system can move, right? While this reference limb right here doesn't move. Just as a for instance, that occurs because of joints. There's leverage associated with that. There's other components to this that will be spoken to later, but now you got a basic idea of the skeletal system. Key concept here is what's known as remodeling. And here comes a couple of terms that you'll really want to know and understand. Just as the neuron is sort of the fundamental cellular component of the nervous system in the skeletal system, we have what are known as osteoblasts and osteoclasts. So osteoblast, and one of the ways I like to remember osteoblast is because it's osteo and starts with a B, not the C. The B, I always think of B, building. So osteoblasts are for building muscles. So remodeling is the formation, development, or growth of new muscle tissue. Again, definition on the side here is the process by which bone is constantly renewed by the resorption and formation of the bone structure. So bones are like other cells, right? They have a lifespan. They break down and then they're rebuilt. We call this remodeling. One of the benefits of resistance training is that you can have a remodeling scenario and the bones get stronger and more dense, something we definitely want to happen for the average person. Osteoclasts, right? I think of cutting. Osteoclasts cut down bone tissue. Osteoblasts build up. So one of the ways, again, I hope that's helpful to understand that osteoclasts break down and remove old bone tissue, osteoblasts that form and lay down new bone. There's a concept here called Wolff's law. That's two F's. And it's also worth understanding that terminology because Wolff's law speaks to this idea of bone remodeling. So osteoclasts, osteoblasts, important to know. On page 127, table 5.1, I would say yes, memorize it. If you have time, it's a good idea to know the different bone types, the long, short, flat, irregular, and sesamoid bones and their characteristics. Always a good idea. And Nazem now will, over the next couple of pages, explain what they are. And it's a good idea to know some examples of the long, short bones. Memorizing every bone like that, not really not that necessary. As you move through short and flat bones, you'll start to get to some more information that you can look at, read through. Not necessary to necessarily memorize it, but it is pretty interesting to understand where these bones are and what their basic functions are. Keep in mind, it's within the long bones of the body that bone marrow is produced. And then bone markings. Now, on page 130 and 131, you're going to get into some more specifics about the bones themselves, such as bone markings, depressions, and processes. The reason these are important, just so you know, is that the way bones are shaped actually is really important. And what I'd like to do for you right now is I'm going to give you an example. And let me go ahead and pull up this whiteboard and just show you real quick something that I think is not only interesting but very important. And this is the idea of what are known as processes. And so what I want to do is I want to show you. Now, remember, bones are designed to be connection points for muscles. So I'm going to just draw an example here for you to help you understand why it's important that you understand processes in these protrusions and depressions. And it's all about, believe it or not, leverage. So if I was, and I'm not saying this is not what you're going to see, if I have a bone with the end, right, in this circular pattern here, and I have a muscle. So I'm going to draw a muscle here, right? Just draw this muscle right here, okay? And if I draw this muscle and I have its tendon attaching to the bone, okay? So there's the tendon attaching to the bone. And let's just go ahead and put the other tendon attaching over the joint to the other bone, right? To another bone. So this is a joint, for instance, and here's the other bone, right? So this tendon would be attaching here, and maybe this is attaching up here at this point. So I want you just to see, because of the shape of this end of the bone, there's a certain amount of, or a certain type of leverage that's associated with the shape of the bone and the position of the tendon and how the muscle and the strength of the muscle can pull. So that's just something I want you to see here. So this is, and by the way, you're not going to see this on the human body, and I'm going to show you why. This has what would be considered to be poor leverage, right? Because of the point of attachment and the way the muscle is shaped. Now, what I want to do here is I want to show you the same thing. Let me draw the bone, right? Draw this other bone and draw you the muscle again. Just again, this is just an example. And by the way, we do see examples of this all over the human body. I'm going to draw the muscle. Okay, there's the tendon, right? So muscle, that is the worst looking muscle I've ever seen, but here we go. Okay, so now imagine though that this bone is not shaped like that other one, but it actually has a protrusion. It's kind of shaped a little odd, okay? Kind of like this, okay? Kind of like this. So here's the end of that bone, okay? So instead of the tendon attaching up the way you see it over here, right? Now the attachment is literally up and over here, okay? And I'm hoping that you get the idea that what I'm trying to show you is that the leverage, the concept of leverage, same muscle, let's just say the muscle is exactly the same, right? In force production, everything. Which do you think is going to have a greater ability to pull? Well, it's going to be this guy right here. It's going to be this guy right here. Okay, why? Because of the protrusion. And so the idea is that given the shape of a muscle, and that's what processes and depressions and all these other protrusions, what are known as tuberosities, right? All of these things, and you know, don't worry so much about the quality of the drawing so much as the concept. It's all based on mechanics. And so the idea is that because of the way bones are shaped, they can affect, tremendous effect, on the ability of muscles to pull and produce force and tension over particular joints. Just keep in mind, I'm just trying to help you to kind of understand a little bit more about what we're dealing with when it comes to muscle shape. So let me go ahead and get out of that. And I'm just hoping that was helpful. You got better pictures in the textbook. Sometimes drawing it out can be a little bit more effective, but we have what are known as processes and tuberosities and other terms that describe the shape of a bone. Again, because of the shape of the bone inside the joint, the shape of these protrusions and the way muscles attach their tendons, they get better leverage. Just real quick, if you think about it, if you ever seen a crane, you know, those big cranes when you know they're building you know, skyscrapers or whatever, cranes are designed on that basic concept of leverage. Okay, so that's why cranes are made and developed in certain ways, so that given given a certain amount of height and other variables that go into the physical makeup of the crane itself, they can maximize the power or force output that they're trying to extract from that mechanical piece of equipment. Your body is very similar in that way, in that the bones themselves are not just straight, straight, and no, they have these protrusions and areas of depression, so that where the tendons attach are going to maximize as best it can, maximize the force or the leverage associated with that particular joint and the muscle. So you get into the vertebral column, and table 5.2 on page 133 gives you an explanation of the segments: cervical, thoracic, lumbar, the sacrum, and the coccyx. So those are the parts of the vertebral column. Remember, the spinal cord is inside, runs inside those, inside and through the spinal column as protection. And then there are intervertebral discs, of course, that protect the vertebrae themselves and act as cushioning devices. Very well, when you look at it just mechanically, it's actually a pretty well thought about machine. Mechanically, it's a really pretty good machine. Mechanically, the way the spinal column is designed with the three curves, that S curve that we see. Again, page 133. Table 5.2, of course, is one of those tables that I would say memorize for sure, but it shouldn't be too difficult to actually memorize this, because you already know probably the three components of the spinal column: the cervical, thoracic, and lumbar. It's normally the sacrum and the coccyx that most people don't know. It's only two other items to throw in there. Not the most difficult to memorize. And when it comes to assessments, by the way, just so you know, the pelvis, right, the sacrum and the coccyx, those areas are really important to know when we're talking about pelvic tilting, right? Comes later on. So understanding joints and what are known as osteo and arthrokinematics. Here we are on page 134. Sidebar, memorize those terms: arthrokinematics. The description of joint surface movement, right, consists of three major types: rolling, sliding, and spinning. What does that look like? Really simple. Don't let it confuse you. Joints do not simply, I'm going to use my fist and the palm of my other hand to simulate, let's just say, the shoulder joint, right? So my palm of my hand simulates what's known as the glenoid fossa, right? The glenoid fossa, which is sort of this concave part of the scapula, which is where the head of the humerus sits in. Okay, so that's your shoulder joint right here. So the shoulder joint is the humerus, right, and this what's known as the glenoid, right, and that's kind of what it looks like. So here and here. Well, joints don't just move this way. They actually roll. They spin inside, and they slide. So all the joints in your body. Now, again, this is not something you can see on the outside. It's just not. Arthrokinematics is this internal, inside the joint. If you could actually see with an X-ray, you would actually notice these slight changes in the way the bone moves in the joint. You're not going to see it. We cannot distinguish this with our eyes just looking at someone when they lift their arm out to the side. But believe it or not, there's not just rotation occurring, right? If you can kind of understand, get a view of what's going on inside my shoulder joint. There's not just the humeral head, right, doing this inside the joint. No, the humeral head is actually moving, it's squeezing into the glenoid. There's a couple of other things, depending on the joint, that's happening. And that's what arthrokinematics helps us to understand. On page 135, for instance, figure 526 explains this this spinning concept, right, of the ulnar radius inside the joint, right? So the joint, right, the head, right, the head here of the humerus and the ulnar and the radius themselves actually spin, right, across that and within that joint. So there's spinning, there's sliding, and there's what we call gliding. Again, if you look at these figures, gives you a little bit better appreciation. And then there's the classification of joints. Are they synovial, which is simply a joint, a movable joint, for instance, that has synovial fluid inside of a joint capsule, right? That's going to be the majority of the joints, your elbow, your shoulder, all the joints that you think about when you're training with weights, right, or resistance are going to generally be synovial joints. Why? Because of synovial fluid located in there. Non-axial joints, for instance. Now, again, page 136, 137, there's a lot of information, and trying to memorize that may not be the most effective use of your time, but at least understanding the way joints function. Because remember, this is biomechanics. Arthrokinematics really comes down to biomechanics. What's happening when people are doing resistance training? What are the forces that are being placed on joints? So understanding this, I remember when I was going through school in kinesiology, and I was a bodybuilder, I really started to appreciate some of what I thought was some sort of esoteric information, when in reality, I'll be honest with you, this was some of, for me, especially when I was dealing, for instance, with athletes, but then the average person as well, that this information was really, really helpful when it came down to basic movement patterns and trying to ensure that I wasn't causing any damage to my clients. So go through it, understand it. Page 137, we have what are known as suture joints, right? The skull, and not a bad idea just to understand that. They're not movable, they don't move, and as you progress from infancy into adolescence, the suture joints on the skull form together and then they lock in place, and now basically your skull becomes a single bony entity. One of the reasons, by the way, that that the number of bones in a newborn is much higher than the number of bones in an adult human is because when you're born, when you're first born, a number of these bones have not fused together. Okay, so in a baby, babies have quite a bit more than 206 bones. Human beings, although we have 206 bones, a number of them are fused together, like in the skull. Function of joints, joint connective tissue. Now, as you get into page 138, an explanation of ligaments, right? Here's your definitional sidebars. Ligaments, collagen, elastin, these are important proteins to know and understand because ligaments are made up predominantly of collagen with a little bit of elastin. Tendons, though, as you'll learn later on, made up predominantly of elastin with collagen with more elastin, and then fascia made up quite a bit of elastin, right? So these are proteins that you do need to know and understand. Ligaments are what hold bones together, right? So you don't just fall apart just standing here. Ligaments are very strong, very powerful. Resistance training can actually enhance and strengthen them. So that's why it's important to understand it. Skeletal system life course on page 138, understanding this concept of growth plates, especially if you're going to be training youth. And so now we get into the exercises impact on bone mass, and we spoke about this before, that there is an increase in overall muscle bone density, right? Bone remodeling when resistance is placed on muscles that obviously connect to the bones. There is a concurrent growth or increase in density of the bones themselves. It's related to two things. The body will actually increase the overall placement of mineral products into the bone, i.e. calcium, magnesium, things like that. And so that mineral increase, that mineral density increase, is one of the ways that the body increases overall density, as well as osteoblast, right, growth and development of new bone tissue. But again, it's that increase in mineral content that really, because bones are made up of two things, right? Inorganic minerals, as well as the living tissue, and they combine together. The bone, if enough of it is in there, calcium, things, phosphorus, the bones get more dense, they get stronger, they don't tend to break as easy, and so that's critical. Now we move into the muscular system on page 140. Again, sidebars, the skeletal muscle, fascia, the epimysium. This is the fascia that covers the entire muscle. What is the basic fundamental component of the muscular system? Well, it's going to be the muscle cell, but muscle cells are structurally composed of other things. And so now, as we come to the end of this chapter, talking about the muscular system, the idea is to understand the structure. Muscles cells. Muscles themselves are pretty complicated when it comes to the actual structure. Very well designed to do the job that they are designed to do, which is to shorten and lengthen and do so under different environmental conditions, and to adapt to whatever you're doing to them. That's the human muscular system. Their main function is to create locomotion, working over joints, attaching to bones. And so some of the definitions here are important: epi, peri, and endomysium. These are, again, like I said, with epi, these are the fascial protective coverings over the different structures. Muscle bellies are structurally composed of what are known as fascicles. And the fascicles are basically just groupings of muscle cells, and they have their own perimysium, and that's, again, fascial covering. Within the fascicles are your muscle cells, and that's the connective tissue that surrounds that, is going to be called the endomysium. And so there's a lot of connective tissue in muscle cells, in muscles. And so you need to know what those are. Glycogen, again, they put glycogen in here, myoglobin, some definitions that's going to get you prepped in some sense when you get into the nutrition. Glycogen is just the storage form of glucose inside a muscle and inside the liver. Here we're talking specifically about muscle cells, muscle fibers and their contractile elements. Now we're getting into the actual workings of a muscle, right? And it occurs at the level of the muscle cell. And within muscle cells, as you move through, you're going to see a lot of these drawings now that give you an inside look at what's actually happening inside muscle cells. We have terms such as myofibrils, myofilaments, actin and myosin. You've got to know what those are. Myofibrils and myofilaments, you notice they start with the prefix myo, muscle. The two main myofilaments are actin and myosin. They are proteins, okay? Structural contractile proteins. They form what is known as the sarcomere, okay? And so these are the terms that are going to help you to understand how muscles contract. So the sarcomere is what we call the fundamental contractile unit of a muscle cell. So as you're reading through this chapter, I am going to once again recommend, and let me show you again what I would do. I would, and I think I've drawn this probably a million times if I've drawn it once. I like to draw this out as a bone, and then basically the tendon and and then I just draw out the muscle, the big entirety of the muscle, right? Kind of looks like this. And draw it yourself, for instance. Look, it doesn't have to be perfect, but draw it out. And then what I do, this is the muscle, right? And muscles are striated. Muscles are striated, right? So I kind of draw it out. You can do this for yourself. And then inside the muscles are what we call fascicles. Fascicles contain, okay, and I'm just going to draw 3 of them, but inside the fascicles are the muscle cells themselves, and inside, right? So you can draw this out for yourself, and it will actually help you to appreciate and understand a little bit more about the workings of the muscle cell. So I'm just kind of giving you a little insight into how I used to learn how to memorize the terms and then understand conceptually what was happening inside the muscle cell. We have what's known as the sliding filament theory, and these are things that that you do need to understand. On page 142, they give you a pretty good figure here on the myofibril. Spend some time. You can always go and look at 3D renderings of these if that helps you. For sure, you can do that. But reading and rewriting the definitions is going to be very helpful. Neural activation, as well as the action potential. Now we're going to pull back a little bit and bring in the nervous system, because neural activation is coming from the nerve, right? And so figure 540 shows you what are known as neuromuscular junctions and how the nerve cell actually stimulates the muscles. Acetylcholine is the main neurotransmitter, where on page 144 on figure 541, just understand this is at a very high magnification, where that what looks like that sort of foot, that's the very end of that's the synaptic cleft right there. So this is where the neurotransmitter acetylcholine is being released from the nerve. Remember, that nerve cell goes into synaptic, these little fingers, these synaptic connections, right? And at the end of each of the synaptic connections, if you blow it up magnification wise, that's what you're looking at on 541. This is where the action potential, which is a neurological stimulus coming from the cell body, right? So remember the cell, the nerve cell, right? The cell body, right? Creates this electrical charge, sends it down the axon of the cell, and that's what you see here. And then it stimulates the release of acetylcholine. Acetylcholine crosses over this synaptic, what's known as the synaptic gap, right? So you got the synaptic cleft, synaptic gap, and then you have these receptors inside the, on the surface of the muscle, and all these cool things happen. Calcium is released in the muscle, and that causes the actin and myosin filaments. There's a lot of really cool, interesting things that are occurring. And if you're getting confused, put me on pause and go back and read through this. And then we get into what's known as the sliding filament theory, which basically says that the actin and myosin filaments, because of the way they are structurally related to each other, they slide over each other under the impulse of the action potential, the release of calcium ions inside the muscle. These actin and myosin filaments are able to mechanically connect to each other, and then they slide across each other through this cross-bridging activity. And there are a number of definitions. The excitation-contraction coupling, again, take a deep breath. Look at it, spend a little bit of time trying to understand it, and you'll start to realize that a lot of these terms are just really simple, basic concepts with big terms associated with them. The excitation-contraction coupling is just the physiological process of converting an electrical stimulus to a muscle contraction. I just said that. The action potential from the nerve cell, boom, hits the muscle, right? And the muscle, boom, contracts. The muscle cell shortens, contracts, right? And that's what happens. That's what the excitation Excitation simply referring to the electrical stimulus, the action potential, and contraction coupling. That means these things are happening, right, in unison, or at least close enough in unison to where they almost look like they're happening simultaneously. We have what's called the power stroke, which is just the myosin head binding. Remember, I said they slide over each other. Probably helpful if I give you a quick little drawing on this and show you exactly what we're talking about. Now, keep in mind, what I'm going to show you here is something that they did not draw for you, but fortunately, I'm going to do it. I'm going to do it for you. And this is at a very high magnification. The head of the myosin, right? So we see myosins, these long stringy proteins, but actually myosins have what are known as tails, which is this part, and heads. And the heads of the myosin, it's actually double heads, right? The heads of the myosin are actually able to flip and move back and forth, okay? Now they do that based on a chemochemical receptor, right, apparatus that really comes because of the release of calcium ions that affects, okay, so these are myosin, okay, I don't want to go too fast on this for you, but these are myosins and they have these heads, and this is where the actual, quote, connection is going to occur between the actin and the myosin. So remember, these guys can swivel back and forth. Okay, let me draw one down here just so you get the idea. Let's just pretend that's the same one. So these myosin heads can swivel back and forth, right? So from here to here, right, they can go back and forth, right? And so if you understand that that's what can happen under certain chemical conditions, right? Let me draw it again for you now and show you. Now, again, this is happening with, lots more myosins. This is the myosin, and this is and now I'm going to show you the actin. Okay, so this is the actin, right? It's not the straightest line. Let me do this. Let me do this. Show you a little bit better. If this is the actin actually have receptors that when calcium hits the receptors, when calcium ions, right? Calcium ions flood the muscle cell, the actin molecule, actually a part of the actin molecule changes its shape and allows the head, right? The head of the myosin molecule, which was like this, right? Remember they were like this. It actually allows the head of the myosin to attach to the actin. How cool is that? When they attach to the actin, right, they can actually swivel and move the actin. Now the actin moves a little bit closer this way. And on the other side, there is another actin, right? And another head of the myosin, right? And these guys can attach to the actin here, right? And when they, remember I told you they can swivel? And when they swivel, they move the actin closer to each other. Now in the middle here is what's known as the Z line, right? Okay, excuse me, this is the A band, pardon me. But they move closer and closer to this middle part right here. And I hope that doesn't confuse you. The idea is not to confuse you on this. The idea is to help you to understand that because the heads of the myosin are able to swivel back and forth, when they attach to it, when they attach to an actin molecule, they can actually attach, swivel, and move the actins in closer to the middle of that coupling. Okay, that's basically what's happening here. And so again, you can kind of replay what I've done there and help you appreciate a little bit about what's actually happening. So let me do it one more time for you, just so there's no confusion. The heads of the myosin are able to swivel, right? So I'll do it this way. The heads of the myosin, right? The myosin tail, myosin head, they're able to swivel like this. ATP is needed, right? And if they're able to do this, but nothing's attached, there's no movement. But as soon as the actin molecule, right, is able to attach, all we got to do is make sure that the actin can attach to the myosin. Well, that's accomplished because of the release of calcium ions, which came from what? The acetylcholine, which came from what? The action potential, which came from what? The head, the body of the nerve sending the impulse down. Boom, 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 boom. Head of the myosin attaches to the actin and swivels and moves the actin a little bit closer to the A band, the inside of the where the tails of the myosins are, right? And so imagine this: attach, swivel. Now here's where the magic happens. At this point, the head of the myosin is able to break away, right, and swivel back. It attaches up and moves it forward. Let me try and straighten this out for you. So if you can sort of imagine what's happening here, it's kind of like a ratchet. That's the way I've always kind of thought of it. So the myosin head breaks away, detaches, moves up, pulls forward, detached, and it keeps moving like this. So you can sort of imagine, I can't go much further. You get the idea? So boom, swivel, detach, boom, swivel, detach, boom. And the actins move closer and closer until they get to the very middle of that A band. They can't go any further. And that's kind of the sliding filament theory. And so there's a number of definitions there that you got to keep in mind. This leads us to what's known as the Moti unit and the all or nothing principle, probably from a purely mechanical perspective. The Moti unit, which is a single nerve cell and all the muscle fibers that it stimulates, probably one of the single most important concepts to know when you're actually training people. So the all or nothing principle simply means that there has to be enough of an electrical stimulus to get the muscle fiber to actually shorten. If there's not enough of that stimulus, it does not. You don't get a little bit of shortening of the actin and myosin filaments. It's either they all connect and shorten, or they don't. And that's where the all or nothing principle comes in. Again, Moti units, single nerve cell, right? And all the muscle fibers that particular nerve cell has synaptic fingers connecting to it. So a single nerve cell with one action potential, think about it now. A single nerve cell can send a single action potential down the axon and literally attach and get multiple muscle cells to shorten and contract simultaneously. That's the concept of the Moti unit. Moti units come in different sizes, of course, because of the number of muscle cells that a particular nerve attaches to. Large Moti units generally are larger nerve cells that attach to more muscle fibers. Just as an example, in your quadriceps, the Moti units, single nerve cell can literally attach to 1,000, 1,500, or even more muscle cells. So one action potential literally affects 1,000 muscle cells simultaneously. You get a lot of power output from these larger Moti units. Moti units in the eye, like the ocular muscles that turn the eye left and right, much smaller. You don't need a whole lot of power, obviously. So those Moti units are going to have maybe 5 muscle cells, 10 muscle cells at most. So every time an action potential is shot from the axon, from the nerve cell, right, it will affect only 5 muscle cells, which obviously generates a lot less power. And those muscle fibers themselves are normally going to be of the weaker, less powerful type 1. And so now you're into, on page 147, muscle fiber types. There's 3. Type 1 and type 2. But the type 2 have 2 subtypes, the type 2A and what are known as the type 2X. If you've ever heard of type 2A and type 2B fibers, um, we used to call them type 2B fibers, but the designation has changed due to some, again, esoteric changes in the enzymatic components and reactions of those different fiber types. It's type 2X now that we use, and not type 2B generally, but I wouldn't get too concerned if you see type 2X and you thought it was type 2B. For the most part, although they're not the same functionally, they are very similar in their power output. So that's all you really need to know on that end. So muscle fiber typing: type 1, endurance; type 2, power, strength. The type 2A fibers are muscle fibers that are sort of in between type 1 and type 2X. And so they have pretty good power output, and they also have a good amount of endurance, right? And you can train them, believe it or not, to be more endurance capable by doing more endurance training. You can train them to be more power output capable by training heavier, more volume type of training. And now table 5.3 on page 148 gives you the muscle fiber typings and their characteristics. I would say that for the most part, you should just know that anyway. You should be able to, with your eyes closed, be able to write down the characteristics of type 1 muscle fibers. And so, yeah, muscular system life course then from childhood to adolescence to adulthood. The muscular system, it does continue to develop. And there are certain issues you got to be concerned about when you train in youth, and certain things you got to be concerned about when you train older individuals. And it's all based on how the muscular system adapts, changes to the environmental conditions that you put it under. And so chapter 5 is really a meat and potatoes chapter that you really want to understand. It still has not gotten really truly in depth to the real world of assessments and program training, but please understand some of these basic concepts and some of the specifics within this chapter, so that later chapters become easier to understand and to also memorize. Remember, you got your summary, and then your basic review. Read through that, go through your chapter highlights, of course, and try and get a real good understanding of each of these bullet points. Again, please keep in mind: read, write, recite. Utilize your pads, paper to write these concept and definitions down. Now that's the end of chapter 5. We've gotten into section 3, which is going to be more demanding, right, conceptually and memorization wise. So we're getting into some areas now that you got to keep in mind are going to require you to be really focused in your studying. Remember, be efficient in your studying and don't get frustrated. If you do, you got to kind of rethink how you're doing your studying. And now I look forward to seeing you in chapter 6.